Okay, welcome back to 6006. We're going to have this problem session. We're doing a quiz 2 review. We're in a much bigger room today, so I have a little bit more board space. So I just wanted to go through what's going to be covered on the exam. First off, the scope. Now, quiz 1 material will be fair game for this quiz, but it's not something that's going to be explicitly emphasized or anything like that, right? You should know that, when we're storing graph data structures, that they can achieve certain running time bounds and that kind of thing. But we're really going to be concentrating on graphs. The 6 lectures that we've had on graphs, the 2 on unweighted graph algorithms, and the 4 that we had on weighted graph algorithms, they covered the material that was covered in the 2 problem sets, problem set 5 and problem set 6. Now, usually this material covers 3 problem sets worth of material. This term, it's covering 2 problem sets worth of material. So just keep that in mind when you're studying and you want to go look back on previous material. Okay. In general, there's lots of graph problems that we've talked about how to solve. There's really a small number of graph algorithms, but they can solve a lot of different problems. Okay. So we saw 2 algorithms to solve the graph reachability problem, single source. What is reachable from me, right? And I can only search a connected component of my graph from me, right? And the connected component from me is actually upper bounded asymptotically by the number of edges in my graph, because a spanning tree of my component has at least, or has v plus 1 edges, right? And so the number of vertices I can reach is upper bounded by the number of edges in my graph, asymptotically anyway. Then we talked about exploring an entire graph, even if it's disconnected, not necessarily from a source, right? Just touching every vertex in a graph. Of course, we can just, touch every vertex in a graph, right? I can look at the adjacency representation of my graph and just go through it. But this is really, we're trying to explore the whole graph, maybe count how many things are reachable from each other in the graph. And this is what we we talked about exploring a graph and counting the size of connected components in a graph in an unweighted graph, right? And we could do this via full BFS or full DFS. It's basically putting a loop around one of these graph reachability algorithms to explore an entire graph by exploring component by component. And when I'm done with a component, I find a vertex I haven't reached yet before and explore it again. Okay? And that still gets linear time in the graph, v plus e. Then we had special types of graphs, directed acyclic graphs, that we could use. We proved this property of, if we ran DFS, full DFS on that graph, we could actually get topological sort of that graph, basically an ordering of the vertices in the graph such that all edges go in one direction with respect to that ordering, like all forward in that ordering, right? And we could actually use that to detect cycles in a directed graph by just looking at the topological sort order and seeing look at the finishing time, the reverse finishing time order of DFS, and just checking to see whether it was a topological sort order, right? Because any back edge there would correspond to a cycle in our graph, because the proposition was that if our graph was acyclic, doing this procedure would give us a topological order. Okay. Then we had an algorithm, Bellman-Ford, that was able to detect and find negative weight cycles in our graph in the way that we've presented it in lecture. But mainly we concentrated on these 2 problems, single source shortest paths, and some a little bit all paired shortest paths, right? First in the unweighted context, and then in the weighted context for the majority of the lectures, okay? So let's move on to what those single source shortest paths algorithms were. We had kind of, to me, increasing in generality here. The first restriction is BFS already solves unweighted shortest paths in linear time. In the unweighted context, that's all good. But for weighted graphs, regardless of the weights, if we had this very strong property on the graph, that the graph didn't have any directed cycles, then we could get this in linear time via DAG relaxation. And then for general graphs, we had these increasing or decreasing restrictions on the weights. First, we had the restriction was that they were unweighted, and that's the BFS constraint, or that they're non-negative. That's the Dijkstra constraint. And if we have no constraints, that gives us Bellman-Ford. And they increase in time. In general, you want to choose an algorithm that's higher on this list, but sometimes the algorithms higher on this list don't apply, right? If on a quiz you come to a graph for which it's not a DAG, but you use DAG relaxation, that's no longer a correct algorithm, right? And so you're going to get fewer points than if you happen to use an inefficient algorithm that is correct, right? So if whenever I saw shortest paths, I used Bellman-Ford, right, is the slowest thing, that's probably going to be a correct algorithm. It's not necessarily going to be the most efficient algorithm, but you'll get more points because it is a correct algorithm than if you apply a faster algorithm that doesn't apply to your problem, because it's not going to solve it correctly. Does that make sense? Okay. So, and then in the last lecture we talked about all pair shortest paths, and really running a single source shortest path from each vertex is pretty good in most circumstances. We don't know how to do a lot better for a lot of these. And then Johnson gives us, basically in this last line of our graph restrictions and weight restrictions, where Bellman-Ford is right there, we can actually get a speed up over v times Bellman-Ford by kind of two tricks, right? Find if the graph has negative weight cycles, and if it doesn't, then there exists a reweighting of this graph so that all the weights are non-negative, but that shortest paths are preserved, and so we can use Dijkstra v times and get that running time instead. Okay? So that's an overview of the contents that we've covered so far. Just want to go, just brief overview of what these algorithms actually do. DAG relaxation, finds a topological order of the thing using DFS, looking at the reverse order of the finishing times. We proved that that's a reverse topological order. And then we relax edges forward in that order because we know that we'll have found shortest path distance to everything before, and we use that invariant to prove that this constructs it in linear time. BFS explores things in levels, right? Increasing in the number of edges as we go out, and I just process all of the ones in the same level at the same time. And Dijkstra generalizes this notion by saying, well, I don't know all of the things that are in the same level, per se, from as I'm going, but I can, using a clever use of a data structure, find the next one I should process in kind of a DAG topological relaxation order to find shortest paths when the weights are non-negative. Because in some sense, I know that once I've reached things from a short distance, I will never have to update their distance again. That's kind of the invariant that we're having with Dijkstra. And then Bellman-Ford essentially duplicates our graph so that each node corresponds to reaching a vertex using at most a certain number of edges. And then that duplicated graph is a DAG, and we can run DAG relaxation. So that's the basic idea of all these algorithms. When I approach problems on a quiz, there's a couple things to keep in mind. There's kind of two things that we have to worry about when you're looking at a graph problem in this class. The first thing is I might not see a graph in my problem, right? I mean, on quiz 2, you know that there's going to be a graph in your problem because we cover graph algorithms on this quiz. But in general, some of the word problems you've been seeing on your problem sets, there's no graph defined for you. They give you an array of things or a set of things or some connections between some things, right? And that might be a graph that you want to make. But kind of defining a graph is an important aspect of that problem solving that is not necessarily something that we've covered in lecture, right? We've not emphasized that in lecture so much, right? But it's something that you've had to do on your problem sets, and it's something that will appear on the quiz, right? So part of this is a modeling context. Can you look at a real world situation, or maybe not so real world, but non-mathematical context, right? And you're trying to abstractify, put it in the language of this class, the mathematics of this class, make a graph, so that solving one of the problems that you know how to solve can adequately solve the word problem that we gave you, right? This is a modeling part. So I always suggest when you see a word problem on quiz 2 or on your problem set, right, it's that see if you can state cleanly an abstract problem related, that if you knew the answer to that abstract problem, you could easily solve your word problem, can make it a little easier to decouple the complexity of the word problem, right? Then you don't have to think about, I don't know, various strange characters we come up with in weird contexts and their weird conditions, right? If you can map that to just a graph with certain properties, and solving an abstract problem on that graph, that might be easier for you to think about and apply the material in this class, so you don't have to worry about, oh, do I have to remember that roads are connected to 5 other things, or do I have to remember, maybe you're given as the input a sparse graph or something like that, right? That's a little easier to think about when applying this material. Okay? And so converting your problem into finding a shortest path problem, or finding a cycle, or finding a topological sort, or connected components, or a negative weight cycle, or any of these kinds of things, right, can make it easier for you to think about. It's not like fundamental material in this class that we need to lecture on, but it is really important for you when you're out in the real world looking at problems to be able to make that transformation from a non-mathematical context to a mathematical. I like to think of this as a modeling part of the problem. But in general, once you've got that nice abstract problem, then in general, you might have a graph, but it might not be the only graph you want when you're solving this problem, right? That might be the input graph that you have. But in general, a lot of the kind of tricks of this thing is not modifying the algorithms that we gave you. If you find yourself trying to modify the algorithms we gave you, that we spent entire lectures on proving their correctness and things like that, that's maybe not something you want to be doing on an exam, because then you're going to be writing pages of derivation and proof that these algorithms work. This unit in particular is much more on the let's reduce to some very powerful black box that we showed you how it works. And so because that's the framework here, the way in which we introduce complexity into problems is to make the graph non-obvious on the thing that you're supposed to apply, right? And so the graph that we give you as the input may be different than the graph that you'll want to use to solve the problem. And here are some strategies that you can use to modify a graph. Like if you want to store state as you're traversing this graph, right? You can expand the number of vertices in your graph to keep track of what state I'm in, right? I can have a different vertex for every possible state I could be at that vertex, right? In your problem session, you had this guy who's drinking when he got to bars, right? Or every third time, and you need to remember how many times it's been since I've been to a bar, right? Or if I had a drunk at a bar. And so you can duplicate the vertices to be able to store that information. Another thing, if you need to search from multiple locations at the same time, or search to multiple locations at the same time, right? You can simulate that without having to run an algorithm many times. You can simulate that by adding an auxiliary node, an extra node in your graph, with edges to those sources or to those sinks, and run a single source shortest path algorithm from that super node, sometimes we call it, to get better performance. It's kind of an efficiency. We're adding efficiency by changing our graph to fit the algorithms that we know how to solve efficiently. And then the last thing, maybe it helps to pre-process the graph in some way, right? Some edges in the graph that we gave you might be forbidden or may need to be traversed in one direction rather than the other, even though the problem statement kind of seems like they should be traversable in either direction, right? And doing this pre-processing of the graph could mean that you break up your graph into your connected graph into a set of disconnected components that you need to find, or makes a cyclic graph acyclic, right? Or prunes part of the graph that you don't want to explore. I never want to touch on my way to get to a location, right? And so these are all really common strategies that we have. Duplicating graph, adding auxiliary vertices or edges to the graph. I don't know the context in which we add edges. It's an interesting question. And then pre-processing, kind of filtering out the graph or transforming it in some way to give it properties that will allow us to solve the problem better. Okay? So any questions about the problem-solving strategies that we have or the content, the kind of baseline content of this class? This is kind of an overview of the lecture type material, where we're not necessarily applying this material in lecture. The rest of this quiz review session will be on applying this material to some quiz from a previous term, some of those problems. Okay? So yeah, you have a question?
What are some common ways that people lose points when they write down?
What are some common ways people lose points? That's a great thing. I'll add it to the notes when we post. So common things that people lose points on in this unit when they're solving problems. You're given a word problem and you don't define a graph, right? It's as easy as that. You start solving assuming that we know what graph you're talking about, when the implicit graph in the problem may or may not be correct, but there's no graph defined in the problem, right? So you need to define a graph in the problem, so that's the first thing. The second thing is, a lot of times it's really useful, just as a strategy, when you construct that graph, tell us how many vertices and edges are in it. Tell us if it's acyclic, right? Tell us what the weights are on each edge. If you don't tell us these things, it's really hard for us to judge your application of algorithms based on that graph, because if there's redundancy there, even if you define for every vertex in my original graph, I have 10 vertices or blah, 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 right? And maybe you're adding a supernode or all these things. It can be difficult for us to follow how many things are. So you do that bookkeeping for us, your graders are going to be a lot happier. Common mistakes: not defining a graph, not specifying your graph completely, and then I would also suggest that instead of just applying an algorithm to a graph, that you clearly state the problem you're solving on the graph first, right? I want to solve this problem because we've given you number of ways to solve that problem on the graph, right? And if you happen to choose the wrong algorithm, then maybe that's separating off the problem from your implementation of how you solve that problem can maybe help you get some points for stating the problem you're solving, even if you choose the wrong or an inefficient way to solve it, right? So that can really help decouple some of the things that we're going to give points on in this class, right? So usually what we're breaking up the graph rubric on grading in: did you describe a graph, right? Did you modify it in a way that's going to help you solve the problem? Did you identify a problem that you need to solve on this thing? Did you use a correct algorithm to solve it? Did you analyze the runtime? Usually involves, is the size of my graph not too large? And what is the running time based on that graph? And then the argument of correctness in this unit is basically like, I constructed a graph that has properties so that shortest paths in this new graph correspond to whatever it is that I want in the original problem, right? Some statement that links the problem you're solving in your problem statement to the problem you're solving on your graph. That's a really good statement to have to bring together correctness. But aside from that statement, you're mostly relying on the correctness of the algorithm, so you don't need to do much on the correctness side. Okay? But forgetting to analyze runtime is a big thing. Okay, so those are a bunch of tips. I'm going to add them to the end of this slide after the lecture. Great question. Any other questions? All right, let's get to solving problems. All right, so these problems that we're going to solve are from Spring 18 Quiz 2, slightly modified, but we're just going to go through them one at a time. So the first problem we have an image of black and white squares. So this is like a pixel grid. You think of it like as a bitmap on your computer, right? And what we say is each white pixel is contained in a blob. Okay, but what is a blob? I don't know, right? Okay, I'm kind of giving you an implicit definition of what a blob is. Two white pixels are in the same blob if they share an edge of the grid. Okay, so this kind of tells me this graph has an edge if these pixels are adjacent and they're both white, right? That's what it means. But an interesting part about that definition is that it kind of is transitive, right? If I have a white pixel that shares an edge with a white pixel A that shares let's start writing things on the board, shall we? Instead of me just talking at you. Right? We have kind of a pixel grid here. Okay, and I don't know how to do this with a chalkboard because it's white versus black. I guess I have to color in the white things. These are all white. All right, so these guys are in the same blob, right, because they share an edge. These guys are in the same blob, okay, but because they share an edge in the pixel grid, these guys are also in the same blob, because if these are in the same blob and these are in the same blob, there's a transitivity argument here, right? This guy needs to be in the same blob as that guy. And then it says that black pixels are not in any blob, okay? And so I'm given an n by m array. I never remember which one comes first, but we have dimensions of this thing as n by m. So we have n times m pixels. And so we're describing essentially a linear time algorithm to compute the number of blobs in the image. Why do I say linear time? It's because for every pixel in my grid, I needed to give you a specification of whether that was white or black, right? And so if I naively gave you the input of this algorithm with a word per one of these pixels, that would be the input size of my, right? And so even though this looks quadratic, right, the actual input size is what we define as linear, right? And so we're looking for a linear time algorithm to count the number of blobs in the image. Okay, so what is this is a little underspecified as a problem, I admit. I hate to admit that I was involved in this class at that time. But the idea here is if these are share an edge, then everything, the observation here is that if I just draw this picture, I notice that anything kind of that's reachable through white connections is going to be in the same blob, right? So this is a blob, and this is a blob, and this is a blob, and this is a blob. But, right, there's no path here. This black part is not part of a blob. Now, actually, there's nothing in this specification that says that we couldn't have these things be in the same blob. Okay, so that's a little confusing, maybe a source of error. This is a source of error that I had when reading this problem after a couple years. But, when you are looking at a problem, if everything could just be in the same blob, then you just return 1 and this problem's not so interesting, right? So the right way to interpret this problem is, I would not need n times m time. I could just say 1, right? So in some sense, I'd like there to be something interesting in this problem, and having these things that are not reachable from each other be different blobs is kind of the more algorithmically interesting thing to have. And so what is this then, right? This is just a pixel grid. There's adjacencies, right? There's connections between pixels. But in particular, I really only care about the connections between white pixels, right? hard to draw on here. But this component has a graph that looks like this. This component is a single vertex. This one's an edge here. And here's a singleton there. And if we were to construct this graph, we would have an unweighted graph such that the number of blobs in my image would be the number of connected components in this graph, right? See how I'm relating the thing that they're asking for in the problem to a property of a graph that I'm constructing, okay? So that's really the key part of argument of correctness that we're looking for, is for you to make some kind of statement connecting the two. Otherwise, you're just constructing a graph, and I have no idea what you're doing to that graph, right? You have to tell me. It's about communication to us. So how do I construct this graph? Well, I can just loop through all of the pixels, right? Look at its 4 neighbors, at most 4, and if those things are both white, then I add an edge. We're going to essentially have a graph. We're going to construct a graph. I told you to do this. Okay. So what is V here? Then V is vertex for each white pixel. Right? And I can just, from the beginning, I can just walk through all the things, find all the white vertices. Maybe I identify them uniquely by their x, y coordinates in this grid. That's fine. Okay? So now I have all the vertices, and now I want to see what the edges are. I can loop through the pixels again and just look at its 4 possible adjacencies, see if any of them are white, stick that edge in this set. So edge is any 2 white pixels that share an edge. Okay? So I can construct both of these things in order n times m, because there's at most that many vertices. I just loop through them. And the edges, for each pixel, I'm only checking a constant number of things, and I'm adding them to a set. So the number of the size of the number of vertices in my graph is at most n times m, and the number of edges is at most n times m times 4, right? It's upper bounded by that because that's the number of adjacencies I have in the graph. Okay? You can probably get a better bound in terms of the number of vertices, right? It can be at most v times 4, right? But that's a little stronger. It doesn't really matter. We're trying to get within the order n times m time bound. So anything's fine here. So that's the graph we construct. And then we can run full BFS or full DFS. We've identified a graph. We've identified that we want to count the number of connected components in my graph. So idea, right? Count connected components. And then, for example, using full BFS or full DFS, right? I wouldn't want you to write both of these algorithms there, but when we write up our solutions, we want them to cover the space of student solutions, and so we will usually mention it. You only have to mention one of them, and because these run in linear time, this also runs in n times m. So all of these things are n times m, and we're golden. Any questions on this question? Yeah.
If I were writing down my proof of correctness and my proof of efficiency for this problem, what sort of things would you be looking for to make sure?
Right. So when I'm writing down, I've described to you the algorithm. And so the question is, what kinds of things do I need to write down when I'm proving or when I'm arguing running time of my algorithm and I'm arguing correctness, right? For running time, mostly just check out the size of your graph, right? State to me what the size of your graph is here. In this case, it's order n times m. And then I state what the running time is of the algorithm that I have is applied to that, right? And so because full BFS runs in O of v plus e time, right? It's useful to actually write this down, even though right? It's not in the terms of our original problem variables. It's useful to write this down so that if I mess up when plugging these variables in, that you're showing your steps, and so if you mess up arithmetically, then we can still give you points. But because the number of vertices in the graph is n times m, the number of edges is n times m, I add them together, it's still order n times m, and that would be sufficient for an argument of running time. And then as I was saying, for correctness, most of the correctness of this algorithm is relying on the fact that this thing counts connected components correctly in my graph. The key observation on a word problem that or even a graph transformation problem is that the property that you're wanting of the original graph or the original problem corresponds to the thing you're solving in a new graph that you've made, right? And so here, an argument of correctness that I would be looking for, that we might allow some weaker statements, is that the number of blobs in the image corresponds to the number of connected components in this graph that I made. Okay? That's really all it needs, but I would like a connection between those values. Okay? Now, why would you be constructing this graph and finding connected components if you didn't if that wasn't what your thought was? I don't know, but it's good when you're communicating to make sure that that's abundantly clear that that's why this is. I mean, you should be able to argue why these things are. That is a connected component. You could say something like, because anything reachable is in the same blob or something like that, right? Okay, so that's problem one. We got these nice mechanical boards. All right, so that's problem one. Problem two is a little funky. Okay. It's been reworded a little bit from from spring 18 so that I could point out some other features of this graph. We're given a connected, so connected is in bold, so that might be an important property of our graph that we're trying to communicate to you. A connected undirected graph with strictly positive edge weights, right? So they're mapping to the positive integers, where E is the same size as V, right? The size of E is the same as the size of V, right? So I have the same number of edges as I have vertices. We're trying to find a order V time algorithm to determine a path from some vertex S to some vertex T with minimum weight. Okay, so what's the first thing I notice? I notice that on this thing I've got a graph. Problem 2, we've got a graph. It's undirected. It's connected. It has this weird property that V equals E, or E equals V, and weights are positive. Okay, and we're asking for a single pair shortest paths, right? We want a path, the shortest path, a shortest path, between two vertices. Now, if we just were given this graph and we want to solve this problem, a very easy way to do that would be to just say, let's run Dijkstra on the graph, right? This is a graph. It has only positive edge weights. Run Dijkstra on this graph. How long does Dijkstra take on this graph? Idea 1, right? Run Dijkstra. What's the problem with this? It applies, right? We're in the context of non-negative edge weights. We can find single shortest paths from S to everything else in the graph in using Dijkstra. It applies. It's a correct algorithm. What's the difficulty with this algorithm?
Too slow.
Too slow, right? That algorithm would run in O of V log V plus E, In this case, these are the same. So this is asymptotically smaller than this one. It runs in v log v. So we're a little off. We're off by a logarithmic factor in our running time. But this would at least be a correct algorithm. Whenever you approach a problem in the exam and you see a really stupid polynomial algorithm that still solves your problem correctly, you might as well write that down in a line. It doesn't hurt you that much to just write that down because it's possible it would give you points for that, right? But on your exam, notice why it is not sufficient, right? Notice that this is v. Notice that this is not the running time bound we're looking for. We got to exploit something different. Okay? Now this is a weighted context. We have weighted paths. It doesn't seem to be in one of the conditions that we can get a linear time weighted single source shortest path algorithm, right? In particular, using BFS, we saw a transformation where as long as the sum of your weights was linear in the combinatorial size of your graph, we could use BFS by making each edge a bunch of undirected edges. We don't have that in this context. And this graph is undirected. So it definitely contains cycles, so we can't use DAG shortest paths. So how the heck can we do this? Well, what does this graph look like? Here I'm going to take a look at this condition, v equals e. Okay? So what does this graph look like? It's connected, and it's v plus e. Well, how many edges does a tree have? V minus 1, right? So in a sense, a tree is the smallest number of edges you can have in a connected graph. So this has one more edge than a tree, right? So really what this looks like, what our graph G looks like, is some kind of tree. And somewhere we've got an extra edge in this graph, right? It's a tree plus an extra edge. That's what our graph is, okay? So, well, let's take a step back. If I just had a tree and I had a weighted graph here, undirected, and the weights are all positive, if any of the weights were negative, how could I solve this problem? Well, every edge is reachable from every vertex. I can just go to that edge and traverse a negative weight back and forth, and my shortest path weight would be infinite for all our vertices. That's not the case we have here. We have positive edge weights only, which means shortest paths are simple. And actually, there's only one simple path between any pair of vertices in a tree, right? I basically, there's one thing I can do. And in fact, if this was S and this was T, that's an X. What am I doing? Okay, T. If I just ran any unweighted reachability algorithm, I would get a tree, right? A BFS tree or a DFS tree, right? It would visit vertices in some order. Now, actually, in a tree, I have to output a tree that connects all the vertices, right? And that would be this tree, right? And so, in a sense, the paths that I got from BFS or DFS in this graph would be exactly shortest paths. I would just have to then go and add up all the path edge weights along the edges. Does that make sense? Okay, so BFS or DFS in the unweighted context can give me the shortest path in the weighted context because there's only one simple path in this graph. But we have a complication here. That's not the question that we're asking. We have an extra edge. And now we have a property where there's not just one simple path to T. There could be two simple paths, right? I could go this way around the cycle, or I could go this way around the cycle. Huh. So that's a complication, but there's only one cycle. If T is over here, there's only one path, right? So if there is only one path, I'll be golden. But if basically the cycle can be reached between these two things, I could have two simple paths. That's the property, right? We have the closest vertex on, so this is the cycle, right? There's a cycle here. If this is the closest vertex to S, and this is the closest vertex to T on the cycle, then I could take either path around the cycle to get from one to the other, and that gives me my two paths. But this path and this path, right, these are completely edge disjoint, right? In other words, any simple path from S to T, if I find this vertex going through here, it can only use one of these edges, right? Because I can't come back to this vertex. Once I go into it here, I got to go out one direction, and I can't come back, right? So it's only one of these two edges. So the idea behind this algorithm is I'm going to find the cycle, or in particular, I'm going to find this thing S prime on the cycle, find the outgoing two edges here, remove one, and then do my tree searching. Basically find the shortest path by running an unweighted reachability algorithm, which will give me a path back to S, the only simple path in that tree, right? I get rid of this edge. And I do that once, and I do it again without this edge. So that's the idea of my algorithm. Okay, so how can I do? I first have to find S prime. How can I do that? Well, I don't know what this edge is, but if I ran an unweighted shortest path algorithm like BFS or DFS on here, I would get back a tree, right? Some edge of my graph will not be in my tree. Something like here, right? The shortest path to this, I look through, I run, so algorithm, idea 2. First, find S prime, okay? And I can find S prime by run, I don't know, a single source shortest path, unweighted, I guess, run single source reachability, unweighted from S using BFS or DFS to explore a tree of my graph. Then some edge is not in my tree of the graph. That will exist on the cycle, kind of by definition, right? It's connecting two parts of my tree. Now I can look at those two paths from here, and the last one that they're in common from S is going to be my split point, S prime. It's the closest one to my source that is on the cycle, right? Because I constructed this cycle here, okay? So I can find edge UV not in the parent tree, right? So maybe this is UV, right? Not in the parent tree. And then find last common vertex in paths from S to U and S to V. Okay, that's going to give me my S prime. Okay, and I can do that by, these are each of linear size, and I can just look at their prefix. I can start from S. I can walk forward until they diverge, and the one before they diverged is S prime, right? That's S prime right here. Once I have S prime, I know what the edges are when they diverge. I remove one of those from the graph. I do the same algorithm again to find a path to T, and I do the same algorithm again to find the path to T, and I see which one is shorter. That's it. There's only two of them, and so I check. Or they could be the same path. in which case my t is actually before s prime on my cycle. Does that make sense? So that's the idea. The last thing is remove an edge from s prime. I don't even have to be picky about this. It has degree 3. I can just run single source sorted paths on all of them and take them in, right? For remove each edge from V, from S prime, remove, let's say, for each edge from S, remove and run SSR from S, okay? And one of the paths there to T will be shortest, my shortest path in the original graph, because it can't use more than 2 of those edges. That's the claim, okay? And this runs in linear time because what I'm doing is I'm running single source reachability once, and maybe 2 more times or 3 more times, a constant number of times, on a graph that has size v, right? And this prefix finding also only takes order v, and so we're done. Okay? Any questions about this problem? No? No questions? All right, we will move on to, what's up?
There's a hint in the title.
There's a hint in the title. Actually, the original version of this problem said, instead of this E equals V specification, it said there's only one cycle in the graph. But it's in the context of undirected cycles as opposed to directed cycles, which is usually what we talk about in this class, right? We say that there's a negative edge weight cycle in the graph if we can, usually we're talking about, we're allowing non-simple cycles in this class. So to remember this property about trees and to enforce this property without talking about cyclicity, I changed the condition for this problem session, this review. Yep?
Could I also just run depth first search on this graph?
Could you just run depth first search on this graph to do what?
Well, to find the shortest path. Right?
To find the shortest path, right? So depth first search on this path, if I ran it from S, when I got to S prime, I would have a choice on what the next outgoing edge to do, right? So if I ran depth first search for one of those choices, I would find a path to T, right? And then I would find, then I could run, and that would find a path to T, right? There's only 2 of them, or at most 2 of them. But then there's the possibility I miss this other path that could be shorter.
Well, how would I miss it if depth first search has to go through the other edge too?
It doesn't go through the other edge. That's the point, right?
Or through the dashed edge.
It won't go through, no. So depth first search will actually go through this thing, traverse an edge, go all the way around the cycle because everything here is reachable from here because it's an undirected graph. It will reach back to here and then backtrack all the way. So we'll actually never traverse this last edge here of the cycle. So it's something you can actually prove with DFS. Now, you could actually, while you're running DFS, try every possibility, right? Because my branching factor is at most 3 at some of these things, right? So what I could do is, or it could be at most 4, right? I could connect 2 things with the same branching, but in general it's a constant, and with every choice DFS could make, I could try all possibilities. How many possibilities would that be? You get a blow up of the degree of every vertex in my graph. The degree time multiplied by each other. That's the number of times I would have to run DFS, which is exponential, right? A constant degree so a constant multiplied like 2 or 3, right? Multiplied v times is 3 to the v, which is exponential in the size of my graph.
But can I have that if the size of v equals the size of v?
Sure, right? Because I could still have large branching for a large number of vertices. Okay? Good, great question. All right, cool. So that's that problem. Problem 3. I have half an hour for the last 2 problems. I think that should be fine. This one's, okay, this is Donut is the problem name. Momar has just finished work at the Fingsprield power plant at a particular location, P, and needs to drive home to a known location, H. But along the way, if his driving route ever comes within driving distance K of a donut shop, he won't be able to resist himself and will have to go there and eat donuts, and his wife, Harge, will be angry. Okay, maybe you can get the reference here. Momar knows the layout of Fingsprield, which can be modeled as a set of n locations with two-way roads of known driving distance connecting some pairs of them. And you may assume that no location is incident to more than 5 roads. Okay, so we've got a degree bound here. As well as the location, and he knows the locations that all the locations that contain donut shops. There's at most d of them. Okay? Describe an n log n time algorithm to find a shortest driving route from the power plant back to home that avoids driving within distance k of a donut shop. Okay, so we got a couple variables in here. We've got k, we've got d, but a running time bound only relies on n, right? Okay, I see shortest paths. I see that I don't see an explicit mention of positive distances of the, I see lengths, right? They say he knows the known driving distance connecting some pairs of locations. So usually I think if I were writing this problem now, I would probably be a little bit more explicit. The distance is positive, but that's, you know, something that you might come into contact with, right? Distances are positive, right? And so we can't have negative distances here, okay? So I look at n log n, I'm like, hey, what has a log in it in this unit? Dijkstra? Maybe I can use Dijkstra. Okay, so let's see if we ran Dijkstra from P to H. Okay, so we've got a graph here. We've got our graph. So this is a word problem, so there's no graph there. So I have to define a graph. Okay, so I'm going to define a graph VE, and we've got V. That's going to be my set of locations. Locations. So this says there are order n of them. There's actually n of them. And then E, what are we going to have? We're going to have, it's a known pair of things, right? Roads with weight equal to driving distance, which by my assumption is going to be greater than 0, right? Now it's not stated explicitly, but you know that would be a reasonable assumption for you to make on your exam, because distances are positive. We would probably be more explicit about that these days. Okay. All right. So this is a graph I could make, and I have a vertex S or a vertex P and a vertex H, and I'm trying to find a shortest path between them, right? Shortest driving distance, driving route, right? Okay, so I could run Dijkstra. Wait, so what do I know about this? How many edges do I have in my graph? I have at most 5 per vertex, right? So this is upper bounded by 5 times V, which is order v. OK, so I have an order v size graph. That's a good thing. Order n, because n is the number of vertices. And so if I were to just run Dijkstra on here from P, doing Dijkstra on G from any S takes order n log n, right? N log n plus n, n log n is bigger than n. OK, so that's a nice observation. We can at least afford to use Dijkstra in this problem to find shortest distances. But what's the problem with a shortest distance found by Dijkstra in this graph? Donuts, like the entire point of the problem, right? I need to avoid being too close to donut shops. OK? So we might have a donut shop here, and we need to stay outside of that distance k, right? Or we might have another donut shop here, right? And so we got to find a path that kind of goes around these donut shops. OK? So in other words, if I have a vertex in my graph where I can reach a donut shop within distance k, I can never visit that vertex, right? Because then Momer will not be able to resist himself and have to go eat a donut. OK? So that's the thing we're trying to avoid. So how can we do this? Well, here's a silly thing. I could run Dijkstra from each of these vertices, these donut shops, find all the things reachable in k driving distance from them, right? And then remove those vertices from the graph. That's an idea. But how long would that take? That would need me to run Dijkstra d times, right? Because there's d donut shops. I got to run Dijkstra d times. So that gives me a running time bound of, I run d times to filter out the graph, right, to modify this graph. And then I do one more to find the shortest path if there is one. But in general, that's going to take d times n log n, not n log n. I have no bound on d except that it's under n. Right? So it could be n, and that would give me a bad running time. So we're going to use a very similar trick here to one of your, I think, a previous review session. Stop. There we go. Is to, when you want to find things, if we're on a prunograph from multiple locations, one of the things we can do is, any tricks? Supernode, right? I can have a vertex. Oh, maybe I don't want to put it up yet. OK? If I have all of these donut shops, what I can do is provide a, I guess these are unweighted, undirected edges, right? Here we can model all of those directed things by two undirected edges. That doesn't really matter. But here, I don't want to be able to go back to my supernode. Okay? But what I'm going to do is I'm going to add a supernode with edge weight, say, 0 to everything else, right? And then if I ran Dijkstra from the supernode and found all vertices reachable within distance k, well, I didn't spend any of that distance going through this first edge, right? And I didn't come back to S because these things are directed into the things. And so anything I reach is going to be within distance k of this donut shop, but for all donut shops. And in some sense, I'm doing this search in parallel. So this is the same trick that we had in the, you're looking through the sewer network or something, and they're trying to avoid monitors or sensors or something like that. We actually did this transformation and then binary searched on a distance. It was kind of involved. But this is an easier example. Now, you can actually generalize this further. What if each donut shop had an amount that Momer liked it, right? So if Momar is within a larger distance of a donut shop he really likes, he still won't be able to resist, right? But a donut shop that doesn't make very good donuts, he'll be able to resist a shorter distance without having to go to that donut shop. So in other words, each one of these donut shops has a different k, right? A different radius that MOMAR will allow. Is there any way to generalize this technique to be able to prune all of those vertices instead? All of these had weight 0 before, the same weight. I mean, the algorithm would have worked for any weight I put on all of these edges, as long as I searched the distance that weight plus k, right? Here, I can just make the distance of this frontier for each one of the donut shops the same by modifying the distance of the incoming edge, right? So I can set the length, the weight to the donut shop with the largest radius to 0, and then put the difference between the largest radius to all the other ones, I put that as the weight on the other edges. And then we still have a graph with positive edge weights, and I can run Dijkstra from S. And that would generalize this problem, and something that we've done in some practice exams or in exams and problem sets in the past. Okay? So that's another common way. So we filter forbidden. There's 2 B's in forbidden, or 2 D's? 2 D's? There's a 3 D's, right? Vertices by using supernode plus 1 run of Dijkstra. Those are the extra letters. Okay, so on your exam, you would probably want to be a little bit more explicit. This is a summary of the things that we just talked about. I just talked 10 minutes about the algorithm. But it doesn't hurt to add a summary at the top of what you're going to write. This is the approach that we're going to have. We're going to filter out the vertices from G, essentially by running Dijkstra from each of these donut shops, but we're going to do it in parallel by adding this supernode. Okay? So actually, on another a recommendation I have for you on an exam is that almost any problem that we give you in this class can get 80 to 90% of the points by writing like maybe 3 lines, right? Almost, and maybe not some of the data structures problems, but almost any question in this class can be solved with not all of the points, but most of the points by just writing a couple lines that we know that you know how to solve the problem, right? And this would be one of those situations, right? Now, I would want, to give you full points, I would want all the details here, that I construct a new graph, I add this vertex here, I have to add edges to each of the D things, but I've only added D more edges and 1 more vertex, so it still has this linear size in my input, right? And then I want to say that I'm putting the weights on here based on what the distance is. Now they're all the same weight because I don't have that generalization. And then I run this thing, and I remove all those graphs, and I construct a new graph from G, right? That's a 3rd graph that I'm constructing now. But notice that the graph that was implicit in my problem was very different than the graph that I'm ultimately running a shortest path algorithm like Dijkstra from P to see if a path exists. Does that make sense? Any questions on this problem? All right, we've got 20 minutes for my last problem. Man, I'm not using, I write much less than some of your other instructors. So I like to talk more than I like to write, apparently. Okay. So problem 4. Let's take a look at this. This one's one I made up last night. Kind of fun. Long shortest paths. Okay, given a directed graph having arbitrary edge weights, basically these could be positive or negative or 0, and 2 vertices from the graph, describe a v cubed time algorithm to find the minimum weight of any path from S to T. Okay, that sounds like Bellman-Ford right there. But I have this last condition. And the last condition is a little weird. Containing at least v edges. So I want a short path in terms of weight, but I want a long path in some sense in terms of the number of edges I traverse. Does that make sense? So of all paths having at least v edges, I want a shortest one among them in terms of weight. This is a weird frickin' problem, right? Usually we're not trying to do this max-min kind of thing. We've got 2 different quantities here we're trying to optimize. Anyone have any ideas on how I could approach this problem? What does this sound, what does the at least v edges sound kind of similar to that we might have talked about in lecture? So when we were talking about Bellman-Ford, we defined this thing called a k edge weight, right? It's the weight of any path using at most k edges. This kind of edge constraint seems similar, except it's kind of the reverse. It's not at least, it's not at most, it's at least, right? Well, here's an observation I have for you. If I want a path that goes through at least v edges, some prefix of that path uses exactly v edges, right? That makes sense, right? So maybe it makes sense for me to, maybe it might make this problem easier if it's not at least v edges, but if it's exactly v edges. Maybe I think about it that way. That seemed a reasonable other way to think about this problem. I knew how to do up to a certain set of edges. Here we're asking for at most. Maybe the thing in between is a little easier to think about. Okay, so what we're doing, we're given a graph, G, it has any weights. It's possible that this graph has E lower bounded by a quadratic in the vertices, right? I have no restrictions on how many edges this thing could be. And so the worst thing I could have is that this thing, I mean, my graphs are simple. The worst thing I could do is have this be quadratic in the number of edges, say if it's the complete graph. That's the maximum number of edges that I could have. And I'm trying to find in my graph a path that uses a lot of vertices, but has small weight. Now, what's another thing to notice here is if I use at least v edges, can my path be simple? No, right? Because I need to use at least v plus 1 vertices, and that's more than the vertices I have in the graph, obviously, right? Now, it could go through vertices more than once, but it's definitely not going to be a simple path, okay? So what's one thing, like, what if there's a negative weight cycle in my graph? What's the minimum weight of any path from S to T if the negative weight cycle is reachable from S, reachable on a path from S to T? What is the answer to my problem then? Negative infinity, right? Because certainly an infinite length path is going to use an infinite number of edges, right? If it's going arbitrarily long, then I can just run Bellman-Ford, right? So that's one thing I can do. I can just run Bellman-Ford on this graph. I have enough time to do that because E is upper bounded by v squared, and I have v cubed time. And if there's a negative weight cycle in my graph, I can know that the minimum weight of any path is minus infinity. I detect that that's the case if basically T is reachable from S with a minimum shortest path distance minus infinity, that the path that achieves that is going to have more than v edges. So, I'm done. And that No path actually achieves that, but that's the infimum, yeah? Supremum or infimum. Sorry, we're going lower bound. I'm thinking of long paths, though. So the number of edges is approaching infinity. Okay? But in the context where I don't have negative weight cycles, actually one of the things we showed was that if you're reachable not through a negative weight cycle, or if no negative weight cycle is traversable from S to T, then my shortest path is going to be simple. But that doesn't seem to apply here either, because we need to have a non-simple path. So what do? So let's go back to this idea of trying to figure out the minimum weight of any path using exactly v edges. Can we use some of the tricks that we had in Bellman-Ford when we're keeping track of the number of edges we're going through at a given time? That's the idea, right? If we have a vertex, if we have a new vertex for each vertex, different versions of it that talk about exactly how many edges I went through, then maybe I could keep track of this while I'm working on this graph, right? So let's say I have multiple layers of the graph. This is the idea. Maybe we start at level 0, down here to level, how many edges do I want? I want v plus 1 vertices. So I'm going to have v plus 1 levels, which is v, right? So a level here. V, how many levels are there? There's v plus the 0, yeah? And so I'm going to have, for every edge in my graph, I'm going to take it. So this is a directed graph, right? So I direct it down into the next level. For each version of this graph that I have, I take that edge that was originally between u and v here in the graph, right? It was originally here in G, but here I've pointed all of those edges downward. Okay? Isn't that what we did in Bellman-Ford? We made one other addition in Bellman-Ford to make it be the at most property, right? What was that transformation we did? We had 0 weight edges going from each vertex to another, right? It meant that we didn't have to traverse an edge, right? But here, if we don't add those edges, actually this transformation gives us that any path that goes through v edges will be some path from a vertex in layer 0 to a vertex in layer v, right? Just because to get down here, I had to traverse exactly v edges, and they're the edges of my original graph. Now notice this encodes non-simple paths as well, right? Because these things I could go here and back to u and back to v and back to u if I had a cycle in my graph. But, right, actually, what kind of graph is this? This is a DAG, right? So this is DAG. Maybe I call this G prime. How many vertices are in G prime? V times v plus 1, right? So I'm going to say order v squared. And how many edges are in my graph? V times e, right? I copied every edge, made it directed down between each level. There are v transitions between levels, and I copy each edge for each of those. So the number of edges is order v times e. Okay, so this graph is blown up. There's a lot of things in this graph. But I notice that, this graph has size order v cubed, is what we're going for. So I can afford to construct this graph, right? Since v is actually also upper bounded by v squared by simplicity, right? Okay, so we have this graph. We could find our vertex S here, S0 up here, and we could afford to compute the shortest path distance to all other vertices using exactly V edges in my graph. Exactly, right? That's what we could do. I can find everything reachable from S0 in this graph and calculate the shortest path down here at the bottom. Okay? So I can do that in V cubed time because dag relaxation is linear in the size of the graph. But that's not what the problem's asking me, unfortunately, right? In particular, I could find the path to t, to tv, and that would give me the shortest path using exactly v edges, but that's not what I'm asking for. I'm asking for at least. So it's possible that I get down here to some other vertex, and maybe there's a negative weight path going to t, and I want to be able to find that. So how can I do that? How can I allow paths to continue past this an arbitrary amount? I could have more layers, right? Right? Actually, simple paths from any shortest paths that are simple, right, that use fewer edges, right? Here I'm not restricted on the number of edges I use, right? So shortest paths in this graph are going to be simple because there's no negative. I can already like throw away the case where I have negative cycles because I ran Bellman-Ford at the beginning, right? I can. So I know that I'm going to want a short path, a simple path, after I've reached v edges, because it's never going to be beneficial to me to come back to a vertex, because that will be a path of longer weight, right? This is the kind of surgery argument we had both in unweighted and weighted context. Okay? So these are going to be simple. So I know that I only have to go v more layers at most. Okay, so that's one way to look at it. I could add more layers of this thing, find the shortest path distance to all vertices using up to 2v edges, right? Maybe even 2v minus 1, but order v. And then for all of the ones down below here, I just look at each vertex and see which weight is the minimum, right? Another way, the way I like to look at it, which is a little bit more fun, I think, is once I'm down here, I'm just trying to find simple paths in the graph from this vertex v, right? To this vertex v, right? So actually, add these, go up. So actually on this bottom layer, right, I want to find short paths to t from actually every vertex, right? And I actually know what the short, just from what I did up here, dag relaxation on this graph, I knew what the shortest path distance was from S0 to each of these vertices, because I did that in v cubed time up here with dag relaxation. So I could add a supernode to this thing with a directed edge to each vertex with the shortest, weighted by the shortest path distance I found up above. Now I have a graph where any path from S0 to v to tv here will be a path that uses at least v edges in my original graph, right? Because these represent the shortest path weights of anything using exactly v edges, and then the path can continue in the original graph, right? So now I have a new graph here, such that every path from here to there corresponds to a path that I'm looking for. So I want to find a minimum weight path in this graph. How can I do that? Now this graph might have negative weights. I can run this with Bellman-Ford. Bellman-Ford. I can do that again. Sure, why not? Now, Jason, why couldn't we just add a bunch of edges here, right? Add our original edges here in the bottom layer of this graph and run Bellman-Ford on this entire graph? Why couldn't I do that? It's too big, right? The number of vertices is v squared. The number of edges is potentially v cubed. Running Bellman-Ford on that huge duplicated graph would give me a v to the 5th running time, which is awful, right? In a sense, we're separating out the complexity. The upper part of the graph has very nice DAG structure. So let's do shortest paths in that DAG structure. And then reduce that complexity down to just being the thing that has the cycles that we are worried about, that reduce the complexity down here. So how big is this graph? This graph has, you know, v plus 1 vertices, right? Because I only added one supernode here. And it has e plus, you know, order v edges. I don't want to be careful here. But this is linear in the size of the original graph. So running Bellman-Ford here only takes v times e time, which is v cubed. So that's two different ways how to solve this problem. One, using a bunch of graph duplication and having the insights that going at most v more steps of this graph duplication could never get a better thing, so I can stop. Or recognizing that, well, I have this very powerful algorithm here that can find shortest paths, simple paths in a graph without negative weight cycles, and I can use this supernote to transfer a part of my graph with a lot of nice structure down to this other graph. Okay? Any questions about this problem? So these are some, we got two abstract problems for you, two word problems for you, with a lot of different transformations and a lot of different tricks of your trade. Any of these would be something that has either appeared on an exam or is at a level of something that could appear on your exam. So go ahead and take a look at the practice material that we've posted and are accessible from previous year's websites, and wish you luck in working on graph problems on your exam.